Alright. Let's try this the third time. Alright. So, I am recording this for Mr. Hills as he is working on electronics museum. And I teach physics. So, I know some things about electronic things. So, let's start out with the one you've already started with, the resistor. So this is a 47 ohm resistor I have pulled from my own collection. It is a okay resistor. It does its job. So flipping over to my notepad. All right. So we have resistors. So resistors, they obey Ohm's law. Yeah. Let's see if we can get an S in there. Ohm's law, which is V is equal to IR. If you go into, there are some other symbols we'll put in here. Sometimes we'll put it in physics. We will do this curly E, and this is our electromotive force. We call it, shorten it up to EMF if we need to. If you get into ham radio, for the reasons I do not understand, they went with a small e. I do not understand. V or curly capital E is my recommendation. Little e, Y, who knows. So this is Ohm's law. V equals IR. You can rearrange it. So V, V is in volts. Little v, named for familiar service, Voltaire. But I just entirely misspelled that. I is a current. It is in amps. For generally speaking, as these are people, capital V, capital A, ampere, and R is in ohms, the eponymous name of this character, of this particular law, named for, well, Gregor Ohm. Units are in little letters, minuscule letters instead of capital letters. Capital letters are people, little letters are units. The symbols, we have capital V for volts, capital A for amps, and capital omega for ohms. So, the point of a resistor, there are a variety of points for resistors. The obvious one is that they resist current. The second one, so most of the time, resistors are not made for the explicit purpose of resisting current, because that will make heat, and heat is generally bad. However, there are certain cases where heat is good, like toasters and heating elements for keeping stoplights defrosted and other such things. But more often than not, resistance is bad, and so we try to not have resistance and resistors. So if you see a resistor, more often than not, it's doing something else. More often than not, it is doing either current regulation, when you see it in its proper context, or is doing voltage regulation. I thought I had another use for a resistor.
Yeah.
I think that's it for what we got for resistors. Those are the 4 uses for a resistor. Most of them are going to be these here: regulating current and regulating voltage. Those are reasonably good uses for using a resistor. Using resistors to make resistance is not great. Making heat. Speaking of, there is a power rule that comes with this. Power is equal to I times V. Well, that means that I can take my Ohm's law here and I can rearrange it and shove it into here, and we find that power is equal to current squared resistance, or I believe, let's see if I do this right, V square over resistance. Power is in this is a watt, but for a guy named, well, Watt. The initial purpose, the thing that made Watt famous was he was working on power from steam engines, and so he's not here because of electricity. He's here because power. And so if we're trying to get power. All right. So there's that. You have a resistor. This is my resistance. This is the voltage drop across the resistor because of the resistance, and this is the power radiated by that resistor because of the resistance. And so ideally, we'd like to keep these as small as possible, unless you're trying to make heat, in which case make it big, but not bigger than you need to, because then you start melting things. Then we have a capacitor. Let me pull out a little thing here. I have a small collection of capacitors here. Flip over the camera. So this guy here, this is a ceramic capacitor. On the front here, you might not be able to see it because the camera's only so good. It says 104. 104 is a marker for how much capacitance that it has. And if I look that up here on my little card, 104, that is 0.1 microfarads. So the first 2 digits are going to be the significant figures, 2 sig figs of the capacitance, and then the last one is the power on the capacitance. So if I flip over to GAMP, 106, right? Is that what was on there? No, 104. 104. That means that this is 1.0 times 10 to the something, minus 4 farads, which is 0.1 microfarads. Farad here, F is, capital F is the unit, spelled out farad. For who's this guy? It was Faraday. Oops, someone spelled this right. Faraday. There we go. So we have a capacitance that is C, and that is Q over V. So that means that V is equal to CQ, like so. C here, this is the capacitance. So that'll be, that's the capacitance, that's in farad. That Q up there, that is the charge. This is a unit of charge here, and it is given to us in, I'm going to spell it right, coulombs. And so this will be in capital C. coulombs. That's rather confusing here. So I got the capacitance in capital C as for the variable, and capital C is the unit of coulombs for the charge. Thanks. Thank you for only having 26 letters in the English alphabet. And so the way a capacitor works, you have a plate here with minus charges on it, and on the other side is another plate with some more charges on it, plus. And so you end up producing an electric field that moves from one side, that points from one side to the other, like so. So that's an electric field, like so. And so, let me see if I can find my equations for the capacitor. Anything else? So, I think the equation of the most interest here is the potential energy stored inside the capacitor, and that is equal to a variety of things. We have 1/2 QV is the energy stored. So that means that we can also store, we can manipulate this equation here, and we get that this is also Q squared on 2C. Yes. And also C 1/2 CV squared. And so there's let's see here. So one of the purposes of a capacitor, there's that, I think at least two. One is to store charge, for backing up the current, basically. The other one we can also store energy. Energy in the electric field. And if I get to the equations for this properly, we can also see that the thing that, let's see here, capacitors will stop. So stop DC current. So what happens is you have your capacitor look like so, and then you put a battery here, and then you got your switch here. And so initially this has no charge on it, and then you close the switch on it, and so then current will start to flow around. And so as the current flows, the charges build up, and eventually you get a voltage here that opposes the voltage here. And so this voltage here will stop the flow of DC current into here. But that also means that we can allow AC current. And so we're basically, this is a filter for AC current, because what the AC current will do is we'll apply a charge to it, or apply a voltage to it, and it'll charge up, and then it'll discharge, and then it'll apply the opposite charge to it, and it'll discharge, and so it goes back and forth, back and forth, back and forth, and it won't stop the AC because the AC will never charge up and keep it that way. Let me see if I grab a hold of my scroll bar here. Nope, that's all right. Come here. There we go. Alright, and so the next thing we have is we have an inductor. So the capacitor looks like that as a symbol here, and so that's the battery. And so we have an inductor. This is how I draw my inductors. And so let me show you an inductor. Pop over here, pop over camera. I don't have a whole lot. I don't know why inductors are so hard to find on the internet to buy and whatnot, and so I have constructed my own. And so this is an inductor I have built around a steel chisel. The problem I've found with this is that I have used a wire that's very thin. And so I can show you why that's a problem soon enough. But the inductance on that is it's a few millihenries. Its actual value I don't rightly know because I built it myself. And so what happens? I'm gonna make a properly sized inductor here, an inductor I can actually draw on. So an inductor like this, if you put some current into it here, some current, so the current will go around and around and around and around and around and around, and go out this way. And so if you use a right hand rule, there's a variety of right hand rules. Grab my camera back. You take your right hand and you put your finger in the direction of, and you take your thumb, put in the direction of the current, and then wrap your fingers around the wire, and your fingers will show you the magnetic field. And so when I look at this inductor that I have just drawn here, where is my? There we are. Flip back to GIMP. And so I think this bit here is in front, and so I put my thumb going down, and I see that my fingers are on the inside, pointing this way with the B field. Like so. And so you get a B field going around. Whoops. It'll pop out this side here and go out that side there, and we're out. And like so. Make a nice little dipole. And so what these guys are good for, and so we have, let's see here, where's all my equations? So the voltage on on an inductor here is negative L, change in current, over change in time. This L here, that is inductance. L is a Henry. So that's a Henry. And who Henry is, I do not know. I don't know who this Henry character is. But we can also store, this is also potential energy. Technically it's potential energy in the field itself. And so this energy is 1/2 L I squared. You probably could rearrange this and substitute things into it if you wanted to. I don't know why. However, where the capacitor up here was to store current, was to store charge. How I think of an inductor is that it's here to store current. And so it's typically, while this is a potential energy stored in the magnetic field, it feels more like a kinetic energy to me, because it's storing the current, the energy of motion of the electrons. And so too, you can store energy in the B field, in the magnetic field. And so things you can also do with it, you can allow DC current. And in particular, because it's storing current in here, another way you could think of it is that if you were to try to cut the power off from it, it will try to keep the current going. But that also means that it is a filter for AC current. And so if you were so inclined, if you have noise in your radio for some reason or another, noise tends to be an AC current thing. And so we will put some ferrite chokes onto the wires, which will act like an inductor. And so it's basically part of, I don't know if we still have it. Of course not. So on older laptops, you get this little cylinder on the DC plug for your laptop, but my laptop doesn't have that anymore. At least it doesn't have it on the outside where I can show it to you. Anyways, surprise. So there we go. So there's the three main passive ingredients to a circuit. Of course, that's not all the equations we can have. So where should I go next? Let's see here. Get rid of all the stuff. There we go. So those are the parts. So we have a resistor. It goes out like this, and then we have a little zigzag, and then it goes straight. We have a capacitor. And just two parallel plates that look like that. And then we have an inductor. And is the curly Q of the inductor. And then we have a battery. Or as my grandpa said, a battery. I don't know how he got that, but he did. Looks like a capacitor, except you can't turn around backwards, and so ta-da. And so this is the plus side, and this is the minus side. What else we got? Let's see here. Let us go with Kirchhoff's laws. Kirchhoff's laws. So what you can Kirchhoff's laws. So that we have his loop law. We have that. Let's see here. Let us have a battery and a resistor, like so. And so this guy will produce a voltage, and this guy will consume a voltage. And so as you go around the loop of a circuit, we have that the sum of voltages going around the loop is equal to 0 volts. As we go around this guy here, we have the voltage of a battery minus the voltage of our resistor, and that is equal to 0 volts, like so. And so we go ahead and solve for V for the battery, and so that means that the voltage of the resistor is equal to the voltage of the battery, like so. But this is equal to IR, which means that the current that's flowing through the battery is VB divided by R, like so. And so there's a current here. So if you want to take a potential energy, and we say, right, we have a voltage and we multiply it by, say, the charge of our electrons. This is effectively the potential energy of a charge due to that voltage there. And so this is actually an energy. This is an energy here. So the loop law is actually a statement. This is actually a statement of energy conservation. So the battery will put some potential into the electron. It comes around and do some work in the resistor, and then comes back around over here, having lost the energy in that resistor. So this is energy conservation. And then we have a junction law. Junction law. It says that the current that comes into a junction has to leave the junction, like so. So we have some amount of current that comes in, and then we have a current that goes out 1, and we have a current that leaves out 2. And so we say that the sum of currents into the junction must be equal to 0 amps. That is the current coming in. Sorry. These sigmas here, these are summing over elements, or yeah, this guy, the loop law is summing over elements, and this guy is summing over the wires coming into the junction. And so we have a current coming in minus a current coming out 1. If I can get 1 on there, there we go. And a current coming out 2. And this is 0 current. So that means that the current in must be equal to the current, oops, try again, must be equal to the current out 1 plus the current out 2. So what this is a statement of, there's a variety of ways to say this. This is current conservation, but there's also number conservation, number of electrons, or you could, and this is also matter conservation. So the electrons that come in have to leave, or the number of electrons that come in have to leave, and the amount of matter that comes in has to leave. And so, yeah, and so. I was going to do a problem. I don't like to. You are making a museum for a general audience. We don't need to be doing actual math problems here. And so we're more interested in what are these things about? How do we use these equations? Well, yeah. And so we're not going to use. We're not going to derive stuff and do problems with them. As a physics teacher, I would love to do problems, but you are an antenna and an informer, and so we will not be doing problems in a constructive manner. What I would like to do now is I'd like to show you a circuit that contains various things into it. So let's see. We have a capacitor. That is not a capacitor. That's a battery. We can put a capacitor, a resistor, and then an inductor here. Let's not just put in a straight line here. Let us put in. Nope. That's not what I wanted to do. Go back to 100%. Did I grab something? I did. Put me back. Give me back my. Thank you. So we have a. I'll put into here an AC source of some sort or another. So, as we go around this loop, you may recall some equations I have written down for this loop. So we have a voltage function as a function of time. It will then go into this capacitor here, and so for it we had that this is Q. This is CQ, capacitance times charge as a function of time, minus a current. Current is a change of charge here, so that's actually dq dt as a function of time, times the resistor, minus the, actually, I believe, yeah, so because that minus sign, that because the voltage of the inductor is equal to minus L change of I over change in time, that means that this minus here makes this a plus. And then, so then L, and then so if this change in current, then it has to be double change in time, double change of charge. So that'll be d square q over dt square equal to 0 volts. Okay, so rearrange this whole thing, move everything to the other side, and so this becomes equals there, plus there, and this becomes a minus, like so. And so what this actually is, function of time, this is actually a second order differential equation, which is a pain in the butt. But obviously I'm doing this from the top of my head. And so I don't find this particularly useful here. Not because it isn't useful. It means I have to solve it out, and like I said, this is for intended purposes. So what I want to do is I want to show you something else about this. So this how about I speak about this? How to do this? This is a ordinary differential equation. They're useful and lovely and all that, but I think it's more interesting to see what happens. Say if I take out the resistor, this goes to 0. Well, then we end up with let's get rid of this guy here. So we actually end up with CQ of t equals L second derivative of Q with respect to time. Oh, there we go. This can be solved out, and we can find that Q here is equal to Q is a function of time. So see, it shows a oscillating circuit here, an oscillating charge. And so you get something that looks like cosine omega t, like so, and so, yeah. And so then we also get the current, even though there's no resistance in here, and so this becomes omega q naught. And cosine is coming down, so I need a minus sign. So sine omega t. And yeah. Well, okay, that's one way to look at it with this differential equation. But the way I look at it is I actually have a potential energy in the electric field and a kinetic energy in that magnetic field. And so we have that this is 1/2, let's see, where was I? 1/2 L I squared. And that's equal to 1/2 CV squared? CQ squared. CQ squared. Like so. And so if you took a mechanics course, it would become very obvious that this was actually a spring, 1/2 kx squared. Oh, not on the side, sorry. A spring would have a, yeah, actually, sorry. I went backwards. My apologies. Let me put it the other way around. So potential energy of the E field with 1/2 CQ squared, and then on this side we have 1/2 Li squared. There we go. And so if we remember from our mechanics, which you did not take, we have a spring 1/2 kx squared, and kinetic energy 1/2 mv squared. And so this should be, if you were to have taken a mechanics course, this would immediately call up a oscillating something. Now, this would be an oscillating mass on a spring. In this case, we have an oscillating current in a circuit. And so we could find the omega, the angular frequency that makes this really happy, and we find that to be omega is equal to 1 over the square root of LC, like so. And so this circuit, without the resistor and without this source here, will naturally resonate with this angular frequency. Let's see if I can double check my. Let's see if we can double check. Yeah, there are. So if we wanted to, more interestingly, we can have a frequency which is equal to 1 over 2 pi. Yeah. Square root of LC. Like so. And so this is the frequency that we think of when we think of oscillating things. And this is in hertz. For Heinrich Hertz. Hertz. The unit being Hertz, like so. Heinrich Hertz, he got his name on this because of his work with radio fields, where he, I believe he actually proved that Maxwell's equations supported radio frequency as a source of light. And so he did that kind of work there. Anything else here? So, if you got rid of one side or the other, let's see here. So, then back all the way up to where I put the equation back the way it was. Come on. Okay, so if I were to get rid of the L, and now I have just the C and the R, so just the capacitor and resistor here, that makes it an RC circuit. And you can solve that out if you want to. And so, let's see here. Do we care about the function for that? I don't think we care so much for that. Do I want to? Okay. So, let's not worry about that too much. So, let us talk about inductive motor. So, my dad has a table saw. So we got a big old inductive motor on here. And so it's got this windings of the electric motor in here. Power comes in, and so this, because of the windings in here, the inductor is going to have a very large L. And so what we find is that the that huge L in there implies a certain is going to produce a certain filter. It's going to be opposed to whatever this voltage is here, this 60, put this guy here, 2 pi, 60 hertz signal over here at a wall socket is 120 volts, right? And so the inductor and its resistance is going to imply, the inductor is going to imply a certain an opposition to the oscillating voltage that we're applying to this. And so to fix this, it's going to oppose that. It's going to try to filter out that 60 hertz frequency. But if we put a big old capacitor on the side here, we wire in a capacitor in here, big old there's a big electrolyte capacitor in here. It's in a cylinder, and so they coil up the have plates in there, the coil in there, and so they put this capacitor here, and so what they do is they make sure that the frequency of this system, CL, they make sure that this is equal to 60 hertz because this is most efficient. So this capacitor will realign will align the current so that the current will be in phase with the voltage that's applied to it, and that will be more efficient. Notice that, remember that the P is equal to IV, and so without the capacitor in here, the current will be out of phase with the voltage, and so the power will be garbage. So instead of having, say, some amount of current, sine omega t, and the voltage will be a V naught cosine omega t. This will actually, right? Can it go all the way? 108? No. Yeah. So you get 90 degrees out of phase, and so this will actually minimize the amount of power you can deliver. And so by realigning with the capacitor, instead of being here with the sine, it comes in with the cosine. And now that they're aligned, you get the maximum power out. And so you're not fighting the current, the power in the line, to do your work. Let's see here. Let's see here. Is anyone else? So this last little bit, the last bit I was talking about here, I would recommend watching a video by Grady Heron. Grady, I forget his last name. Let's see here. Practical engineer. Practical engineering. Power efficiency? Let's try that. Is that here? Yes. Yes, this is the one. Great. Stop. Stop. Just stop. Thank you. So this little bit here that I was talking about, I would recommend you go pay Grady at Practical Engineering a visit. At, let's see here, Z little w little k NT little w big W big J big P 5 K. And the title of this video is the most confusing part of the power grid. This video would probably be a better discussion of what this mess here is, as he is an engineer. Anything else I want to talk about that might be of interest to your museum? Oh, right. I would like to explain why that tiny wire on my inductor is so bad. Come here. Right. So, actually, let's get rid of all this. Get rid of all that. So, just tap on the right thing. So a resistor, the resistance in a resistor is also equal to where'd it go? Where'd it go? Rho L over A. So if I have a wire that is a certain length, so it's L long, and it has an area, and so it has an area here, an area here. So it's L long and it has a certain area. So rho here, rho is, rho, try that again. There we are. This is the letter rho. This is resistivity. It is a unit of, it comes in units of ohm meters, and it is basically the bigger this thing is, the bigger this value is. It's material dependent. The bigger the value, the more resistance you have in your material. Now, copper has very low resistivity, and so we make wires out of it. And so, but it hasn't. The wire has a length, and there's not much you can do about the length. But the area here, this area is problematic. So with a tiny area, this means that small area, which is a function of the, radius of the wire, pi r squared. A small area implies that the resistance is large. And so when I had written out that big old equation there, Q, let's see here, CQ plus RI minus L delta I over delta T equals 0. And so if you were to actually look at this guy here, what you find is that because of this resistance, this has a damping effect. And so when I put, one of the things that I like to do is I like to try to show students oscillations, because the simple harmonic oscillator that mounts on a spring, the capacitor and the inductor together without anything else will repeat themselves over and over again in various levels of abstraction, all the way up to nuclear physics, high energy physics, all that kind of stuff. With the particles in quantum mechanics, it's the simple harmonic oscillator is kind of near and dear to my heart as a thing, and so I'd like to show students an oscillating circuit. The problem with my inductor, with this really fine wire there, is that implies about an ohm or two of resistance, which means that I have to, in order to have an oscillating circuit, I have to make the capacitance really high, which means that when I get done with it, this voltage as a function of time, I can excite an oscillation in my circuit, and it will do this number, like about so, and this interval here turns out to be like 2 nanoseconds. I have a Hewlett-Packard 1722B oscilloscope from the 1960s, which means it has a CRT screen. It can do nanosecond scale circuits, but it can't show them very well because the electron beam is flicking across the screen so quick, and so you can't hardly see anything because it doesn't have time to, excite the phosphors in my screen. And so this is rather quite disappointing because of this damping means that my oscillation is really short. And so if I get the opportunity, I'll remake it with a bigger wire so that it will extend out. This is also a kind of problem with ASUS motherboards. They have the normal working state, and then they have a conservation state. And so what happens is that you have a voltage going to your CPU that then suddenly drops, like so. So this is the working state, and this is the C state. ASUS has done a poor job of implementing this, and so what happens is that there's not enough resistance in the circuit to damp out what happens next, and it will come down, straight down, past what it wants, back up again, and up and down and up and down, and it'll ring out. And the CPU says, I don't like this up and down business, and it freaks out and it stops. It immediately stops doing whatever it's doing, it locks up. This has happened to myself, and also Linus Sebastian at Linus Tech Tips. And so, so this would be what is known as an underdamped circuit with too little resistance. You can overdamp it, where it will pass by once and then bottom out like so. This is overdamped, and then you can have it where it is critically damped, where it will go down and then it'll come up once more before settling out here on top. And so you can use this resistance to dictate the amount of damping you have there. And so they need more resistance in their motherboard somewhere. Alternatively, they can make it ring at a lower frequency, and that'll probably also fix it. Or they could try to take a ramp on their voltage that they're applying, rather than a sudden step function. This would probably also help them out a fair bit. Or they could not enable it on their desktops. They should just leave it flat on their desktops, which is what I've done to mine. That's why Linus fixed his. The C state, the conservation state, is really good for laptops, but it's not so critical for a desktop that's plugged into the mains wire. Anything else? No, I think that's enough. I think that's enough for now. So I'll go ahead and stop that, and you can tell me if you want something else.